Death Valley in the United States. It's one of the hottest and most hostile places on Earth. Here, our team of 5 scientists will face their ultimate test, a series of challenges all about space exploration. Our 5 scientists are Kathy Sykes, an irrepressible physicist who thrives in the face of adversity. Iain Stewart's our first rough science geologist and an eternal optimist. McCallie is an intrepid botanist from Missouri with a never-say-die attitude. Mike Bullivant's our creative chemist who makes magic with everyday items. Jonathan Hare is a physicist, inventor, artist, a true Renaissance man. And then there's me, Kate Humble, here to lend a hand. Together, we are Rough Science. Mission Control is an abandoned silver mine on the edge of Death Valley. Here the scientists have basic kit and simple tools. Ingenuity, they supply themselves. This week, we're looking at things that fly around in space and the impact that they have quite literally on Earth. Because, Iain, Kathy and Mike, in Arizona, a huge meteor hit in the desert, causing one of the biggest impact craters on Earth.
Excellent.
What we'd like you to do is to use your science skills to find out just how big that meteor was.
So we're going to Arizona?
You are. You get to go to Arizona.
Big meteor crater, yes.
Now, Ellen and Jonathan, it's not just the Earth that gets hit, the moon gets hit as well.
We're getting on the moon!
Yeah. If you can come up with a way of getting there, that's absolutely fine, because what we'd like you to do is to find a crater on the moon, anyone you like, pick one, and tell us exactly how big it is. And because you're going to be working at night, Ellen, maybe you could come up with some sort of lights that are going to be bright enough to work by, but not so bright to obscure the night sky. Yeah. OK? Now, you've got 3 days, as usual. You've got the workshop, everything around here to use, and, of course, the glorious magic trunk.
Ooh. Flower.
So are you two going to build a rocket and go to the moon, then?
It would be nice, wouldn't it?
It would be fantastic.
I don't think we have enough time, though.
No.
But we are going to build something that's going to make the moon come closer to us.
We've got all the bits with a very bare minimum to make a telescope.
And will a basic telescope be strong enough to look at craters on the moon?
Should be, yeah.
Really?
Yeah.
And then once we have a telescope, we can observe the moon and its craters well enough that we think we can figure out the diameter of one of them.
The moon is almost 400,000 kilometers away, so it's going to be pretty impressive if they can make a telescope that can see a crater in enough detail for them to measure it. The Arizona crater is a bit nearer, but it's still a 4-hour flight away, so Mike, Kathy and Iain are going to need some careful planning to meet their challenge. How are you going to find out how big this meteor was?
Well, we've decided that it's pointless all 3 of us going to Arizona.
Right.
It's important that Iain goes. He's a geologist, so he'll get more out of the
He'll
experience.
see loads of things that we would never see.
OK.
There should be some clues there, I think.
All right. All right.
Kathy's good at measurement.
We've got to go actually see the crater and measure the diameter, so see how big that hole is.
So it looks like I stay behind here. But
What are you going to do?
Well, I can make my own crater. I don't need anything out in Arizona. I've got flour, I've got marbles, I can play around. So I can see if there's any relationship between the size of the marble and the size of the crater that it forms.
So the Meteor Crater team are going to split up. Iain, Kathy and me have got the fun bit. We're off to Arizona to measure the crater's diameter. Mike's making dozens of his own craters to work out what factors affect their size. Kathy and Iain's job is to accurately measure the size of the Arizona crater.
I can see it!
It's over there! Oh, it's huge!
Look at that!
Oh, my God, that's amazing! We're just about to go over the moon! That's just amazing!
Mike will use the size of the real crater to scale up his miniature experiments and so predict the size of the meteorite. And he's found a heavy iron ball, which he hopes will produce more realistic results. Jonathan and Ellen want to make a telescope, but all they could find in the trunk was an eyepiece and something that looks like a shaving mirror. So how are they going to do it?
We're really lucky because we've been given this, which is a rather beautiful mirror. So this is actually got a curved surface on here, and on the front of this glass is an incredibly thin layer of aluminium, which forms a mirror. And what happens is light comes in, hits this mirror, and it's focused to a point, just like it would be with a magnifying glass lens.
Or then we can put our eyepiece.
And get a really crisp, beautiful image.
Yeah.
Yeah.
Oh, wow.
Meanwhile, we've arrived at the crater in Arizona.
Look at that. That's fantastic.
Iain's in geology heaven.
Look what I've got for you. Look at this. Stuff from space.
No.
Look at that. That's fragments of our meteorite.
That's the meteorite that caused this crater.
Yeah. It's made of metal. It's iron and nickel.
But that's not the only sign of the meteorite that Iain's found.
What do you think of that?
Oh, it's all good groove.
Yeah. Well, the thing is, this is what it should be. This is the sandstone that sits at the bottom of the crater.
Yeah.
And this is the rock that you find just all the way around here.
Yeah.
And what this is that this is the sand that's been thrown up by the impact and just pulverised, so it's powder. Watch this. You can just crush it.
Good groove.
So, hang on. Are you telling me that when the meteor hit this rock, it hit it with such force that it turned it into basically talcum powder?
It was an enormous force. In fact, I've got something else even better. Look at this here. Just up here.
Look at him, it's like a mountain goat.
Look at this thing.
Well, it's a rock, Iain.
It's it is an enormous rock. The thing is, this limestone rock here has been down there in the crater. And the impact, the explosion, has thrown it all the way out here. And it's enormous. It's the size of a house. And there's loads of these blocks around here. I mean, this must have been an enormous explosion.
Jonathan and Ellen are using their mirror to make a telescope, but they need to work out where to put the eyepiece. It all depends on where the mirror is focusing the image, and they're using the sun to guide them.
We've got a ruler here marked off in centimetres, and we should be able to get an image of the sun on this bit of paper. Where are we?
Yeah, there it is, yeah.
Beautiful.
Ooh, that's good, that's good.
Oh, yeah, and there's so much energy there, you can see it. Look, it's enough to light the paper. So that, according to our scale on here, is about 120 centimetres. That's where it's sharpest, the image.
Right. Yeah. So if we want a really sharp view of the moon, we want to put our eyepiece there.
Yep, right.
Okay.
Great.
So the eyepiece has to be 120 centimetres away from the mirror, where the image has its sharpest focus. Mike's doing his best to make his experiments as realistic as possible.
I've just spent the last few hours dropping our ball into a new medium. I'm using sand instead of flour. Sand is obviously what's in the Arizona desert, so it's closer to what actually happened with the real meteor. Yeehaw.
He's also trying to increase the energy of the impact by dropping the ball from a greater height.
3, 2, 1. Yes! It bounced!
It's day 2. Kathy and Iain have to get an accurate measurement of the size of the crater to give to Mike. Kathy's decided the best method is to make a scale drawing of the crater.
Now imagine this circle here is representing the crater, and we want to measure the diameter, so this distance across here. One way to do that is to use a baseline, and we've got a baseline of 100 metres. So we're going to have two little points like this at the edge, 100 metres apart.
We're running out of space here.
Kathy, Are you happy with this as a baseline?
Yeah.
Okay.
All right.
So take up the slack.
Keep it taut, Iain.
And what we can do is line up from this position here, from this tripod, to a point that seems to be on the opposite side. Kind of take a sighting.
Yeah.
And use our protractor to measure this angle here. And that angle we'll call angle A. So it's just 2 degrees off 90, so that's 88 degrees.
Okay.
And then walk the 100 metres with a bit of string that we've got and measured out. And then we do the same thing over here from this point here, and we call that point B. OK, so we just have to line this one up to the same point over there. And it looks like it's...
87.
Just to be sure, she does the whole thing all over again from the other side. Now it's back to the mine, where she can transform the 2 angles and the baseline into the diameter of the crater. Jonathan and Ellen now know where to put the eyepiece for their telescope, but they're still missing something. A peculiarity of mirror telescopes is that they need a second, much smaller mirror to reflect the image into the eyepiece.
Yesterday we worked out where the focal point was for the mirror. And we've added another mirror here, so it's a second mirror, which bends that light to where the eyepiece is now. And we've got arranged a little jig here, which allows us to move it and therefore focus it.
And that actually makes sense, because if we didn't bend it at a right angle, we'd be trying to look at an image here, and we'd also have our head here, so we'd block everything we're trying to see.
Yeah, you'd have to have the eyepiece there, which would be just crazy. So this is quite nice.
Yeah.
Although it's a bit odd, because you seem to be looking through that way at something in that direction.
Yeah.
It's a bit strange at first. Let's see if there's anything there. Oh, yeah.
Everyone's back from Meteor Crater, and it's time to compare notes with Mike. We've got the measurements to work out the crater size, which is what Mike needs. But Iain's also got some less welcome news.
The problem, I think, is what we saw at Meteor Crater was that the energy was so large that that thing had been shattered. So there is no meteors sitting in the middle of the crater. It's just been blasted apart.
It's big explosion.
So we need much bigger energies than...
Iain thinks that the explosive energy of the meteorite impact means that it may not be possible to scale up Mike's results to predict the size of the meteorite. His experiments just didn't have enough energy.
We need something like a cannon blasting a giant iron ball as fast as possible and exploding into rock.
Something like that.
Anything else? Okay, bring us a cannon.
So Kathy and Iain think they need an experiment to mimic the explosive force of the meteorite. Perhaps Mike's been barking up the wrong tree. Meanwhile, Ellen's gone off in search of something that might illuminate their nighttime measurements.
It's up here in the mountains that the pine trees grow, and I want to collect some of the resin. I think the resin, if I mess with it enough, I'll make some really good candles for Jonathan and I to measure the craters of the moon by. The Native Americans used resin for almost everything. It's great for sealing pottery. Of course, if they were traveling at night, they'd put it on sticks and then light it. It was a great torch. Oh, look at this stuff. It's really gummy stuff, the fresh stuff. Supposedly, it was really good as a lozenge if you had a sore throat. It's quite nice.
If you say so, Ellen. Meanwhile, Mike hasn't given up hope of rescuing his low-energy experiments. He thinks he can adjust his results to compensate for the massive power of the meteorite impact. But he needs to know exactly how fast it hit the Earth. Luckily for him, we have a geologist in our midst.
And how about the velocity of our meteor?
Well, typically they come in at 20 kilometres a second.
20 kilometres a second?
Yeah.
It's about 30 times faster than Concorde.
Knowing the meteorite's speed and with some nifty maths, Mike thinks he should be able to put his iron ball experiments back on track. It's just going to be a little more complicated than he first thought. Meanwhile, I couldn't find a cannon for Kathy and Iain, but I could find a cowboy, who's the local gun expert. Iain and Kathy think that even though a bullet is tiny, its high speed means it will make a very big crater. And because the real meteorite was also travelling very fast, this will be more realistic than Mike's experiments. More bullets equals more data.
Wow.
Hey, it's bigger, a lot bigger.
Even though the bullets are tiny, they've both made large craters. So Iain and Kathy think that the real meteorite would also have been much smaller than the crater it left behind.
Wow.
The sun's gone down and it's time for Ellen and Jonathan to set up their telescope. But is it powerful enough to identify individual craters on the moon?
Look at that moon! Can you see it through there?
It's beautiful. Come and have a look.
You can't. Can you see it? Really?
Oh, yeah.
Oh my God! I can't believe it. That's incredible. It's so clear. There's so much detail.
It's so beautiful, isn't it?
The moon looks great, but now they have to pick a clearly recognisable crater, one they can find again tomorrow night.
As we see it through here, at the bottom, there's a really big, beautiful crater. But it's quite near the rim. It's quite near the end, if you like.
But it's not quite at the bottom.
No, that's right.
That's Plato.
Because there's not many big ones down there.
Yeah, that's Plato.
Okay.
Go
now,
on.
if you go up from there, so a third of the way up, there's another one with two little craters next to it, and it's beautiful.
Archimedes.
That's Archimedes?
Yeah.
Excellent. That's the one.
Yeah.
Why are you going for that one, not the other one?
Well, the thing is that the other one's sort of on the edge, so we're not looking at it straight on. But this one, you're almost looking on straight on, so hopefully when we measure it, it's going to be the proper dimensions, not some distorted dimension, you see.
So Archimedes it is, but the challenge looks even harder now they've found a crater. It looks tiny. By the time the sun has risen on our last day, they're ready to reveal just how they're going to do it.
Well, all the objects in the night sky appear to move across the sky because of the rotation of the Earth.
Yeah.
So when we look for our eyepiece,
Yeah.
the moon actually is going to go across quite quickly.
Okay.
Now, if we have some reference point, we can time how long it takes for the moon to go past that reference point.
Yeah.
That's
And
our first measurement.
Right, and because we know that the moon is 3,500 kilometers across,
Yeah.
we can then time how long it takes Archimedes to cross that same reference point and calculate the diameter of Archimedes.
Okay.
So if it takes 10 seconds for the moon to go across the reference point,
Yeah.
it takes 1 second for the crater, we know it's a tenth of the size.
Brilliant. Absolutely brilliant. Kathy's working on her measurements from the Arizona crater. She's about to turn 2 angles and a baseline into the diameter of the crater.
Now, give me a figure.
It's 1,200. But look, scientifically, it would just be completely wrong to say it's 1,200 because it varies so much.
Okay.
So you have to give me that. It's 1,200 plus or minus 300 or 400
Fine.
meters.
So we have another piece of the jigsaw, even if it is only a very rough estimate from Kathy. Jonathan's finishing off the telescope. He's putting one of Ellen's hairs across the eyepiece. This will be the fixed reference point they use to time how long it takes the moon and the crater Archimedes to cross the eyepiece. They're going to need split-second reactions. Ellen's trying to make longer-lasting candles. She's refined the resin, and by mixing it with clay dust, she's hoping to slow down the burning. For the Arizona Crater team, it's time for the final showdown.
Your challenge was to try and work out what the diameter was of the meteorite that caused Meteor Crater. And of course, one of the first things that you needed to ascertain was what the diameter of the crater was. So, Kathy, we
measured the diameter of the crater to be about 1,200 metres, plus or minus 300, which we've marked, that's this point on the graph here. Then, using Mike's experiment with this thing here, we gave a beautiful straight line, which gave us a meteorite size of about 30 metres.
Okay.
Okay? The gunshot experiment shifted that up a bit, say to about 100. So we'd like to give you a range between 20 and 110 metres for the meteorite size, because we still have big errors in there.
Handily, I have a letter which reads, Dear rough scientists, Meteor Crater has a diameter of approximately 1,200 which is just too mad. However, it goes on. We don't know exactly how big the meteorite was. We do know that it was much smaller than the crater. After extensive research, our best estimate is that it was between 50 and 60 metres in diameter. And that letter comes from Dante Loretta, assistant professor at the Lunar and Planetary Laboratory, University of Arizona.
Well done, Dante.
So, if you write to him, he might give you a job.
Excellent.
Mike said 30 metres, Iain and Kathy said 100, and the answer is somewhere in the middle. I think we'll call it a draw. But the hardest measurement is still to come. Can they work out how big the crater Archimedes is? Ellen's candles are working a treat, so everything depends on split-second timing. Jonathan and Ellen have already timed how long it takes the whole moon to cross the Hare in the eyepiece. Now they're timing how long it takes the crater to cross the same point.
Now.
5.35.
Tell me when you're ready, Jonathan.
I'm ready.
Now. Now.
OK, this is getting better now.
OK, Jonathan and Ellen, here we are, sitting in Ellen's candlelight and waiting for the results. Have you done all your calculations?
We have.
What is the diameter of the crater of Archimedes?
So after going through all the maths, the result is that it's 72 kilometres plus or minus 10 kilometres.
OK. Well, when you told me last night that Archimedes was the crater that you were going to measure the diameter of, I spoke to Dr. Robin Catchpole, who is the senior astronomer at the Royal Observatory Greenwich in London, and he told me that the diameter of the Archimedes crater is 82 kilometres. So they were only 10 kilometres out. Pretty good, I'd say, for a crater that's nearly 400,000 kilometres away. Absolutely. Yeah, I think that was pretty good. Well, that's all for Rough Science for this week, but join us next time for more.